Yeah, Nirant, I think we are good to go.
Okay, okay, start up. So hello all. First of all, thank you, Shreyansh, for accepting our request to come to RoboReG Talks on a Saturday morning. And so, main motive of this talk is to brief undergraduate robotics researchers about the life of roboticists and the work they do as a part of the research. I think we've been planning for this like for a real long with Shreyansh, and we're really desperate to get him to talk on our platform. And finally, this is happening. So thank you, Shreyansh, for coming. So yeah, I think we can start with a formal introduction. I think I'll pass it on to Vinod.
Yeah, thank you, Nirant. So, welcome all, and for people who are not a part of RoboReG, so it's our duty to probably introduce ourselves. So, I'm here to do that, and I think the slide should have updated now. So, yeah, so RoboReG, so we are the robotics research group. We are kind of a wing of the robotics club, which entirely focuses on. We are a group of robotics enthusiasts, to be very frank, and we actively investigate different domains of robotics. So what we do different from a traditional club is that our main focus is to carry out previously unthought projects, undone and untested, through our novel approaches, basically. So at present, mostly our work is revolving around learning-based techniques and planning and control and things like that. However, we tend to address like different domains of robotics aspects. Like if you are able to see the slide now, so these are kind of some of the projects that we are currently been up to. So we have legged robots, we have multi-agent systems, we have simultaneous manipulation robots, and we have autonomous decision-making systems. So the end of the day, what we try to address is we have something to contribute to the robotics community, which is not exactly existing previously. So that is our primary goal. And at present, we are functioning as a part of a robotics club, and future will be extending as well. So what we look forward being a research group is to collaborate and possibly bring in the diverse set of knowledge from around the world. So we try to communicate, we try to network with people from different domains who are actively having their research being done in the frontiers of robotics. So at present, as I mentioned, we have tried investigating different domains, but robots in space is still a new thing for all of us, and it's pretty inspiring as well to begin with. So we wanted to have a great start on that, and we actually wanted to get to know it better, and who to hear it better than a person from NASA itself. So we have Shreyansh with us to share his work in the same domain. Before I just hand it over to Shreyansh, I just kindly request all of you in the meet. Probably this is kind of an obsolete instruction, given that we all have shifted to the new normal in the past, normalcy in the past 1 year. But I kindly request all of you to be muted to have a very smooth webinar. And probably you can preserve your questions for the end. And like if you have any questions then and there, it wants to be immediately addressed, you can put it in the chat. And also towards the end, so the session is divided into two parts. The first part will be Shreyansh's presentation, followed up by an interactive Q&A session. So during the Q&A session, I just request all of you to use the raise hand option before actually unmuting yourself, so that we can have a very ordered talk. So on that note, without further delay, I'll hand it over to Shreyansh. The stage is yours.
Thank you so much, Lokesh, Pratyush, and Nirant for the introduction. Let me share my screen. You guys should probably be able to see a blank screen at this point.
Yep, visible.
Okay, Can you guys see my slides?
Yep. Yep.
Okay, great. Yeah, so if for some reason there's an audio video issue, just somebody unmute and stop me because I can't see the Google Meet anymore. Okay. So hello guys, thank you so much for joining in, and thank you for the team for inviting me for this talks and the introduction. I'm a research scientist slash robotic technologist at NASA's Jet Propulsion Laboratory. As these guys mentioned, it's my honor to be here. And in today's talk, I hope to share with you my excitement about how the use of AI and robotics is enabling new frontiers in space exploration. Before I start, I want to uh, just say a word that it's really great that you guys are doing this. It's actually very inspiring, and this is great. I wish I had some of this, the option to have some of these exposures, talks, even a robotics research group when I was in undergraduate at 8 to 10 years back. And I think the culture there was really not so much where a big group like this is trying to do some very collaborative work together. So I think the fact that you guys are doing this and even during COVID is exceptional, and that's kudos to you all. So let's get started with that. Before I jump into the AI and about the work, I wanted to maybe start with a brief overview of the journey, just because I know most of this population is student population, and they're probably really interested in the journey part. So I don't have, I'm not going to go too much into that, and I think most of this was really covered already. This is a single snapshot of my journey in a way. I'm born and brought up in Kolkata, which is the rightmost start. I did my schooling there, and then went to Manipal Institute of Technology for my undergrad, where I studied electronics and communication engineering. During that time, I spent a lot of time learning more into robotics. Even though there was no robotics research group, there was definitely a community coming up who was trying to do a lot of work, who were trying to do hands-on robotics. So I tried during college, I was very proactive in trying to learn more and get deeper expertise into robotics. And I'll briefly be showing that in the next slide. I did a lot of internships actively, tried to pursue them. Obviously, it was hard to find them initially, but then things get easier. So I did an internship during the summer at Carnegie Mellon, but then I also spent a year after that at TU Graz, which is one of the top labs in aerial robotics and computer vision in Austria. It's one of the best labs in the world. I was very fortunate to work with really good people, do some really good work where I was preparing myself for grad school before applying. And fortunately, I did get accepted at Carnegie Mellon, which is one of the best places you can do robotics at. So I did a master's there, and right after that, again, I was lucky enough to get my dream job at NASA. So that's roughly my journey in a very 1 minute description. From a robotics perspective, what really prepared me to get there was a lot of hands-on experience. So this is a very just a single slide video snapshot of the kinds of robots I worked with, I developed uh, as part of either what I was doing, but most of this is actually part of internship work that I was doing. Uh, so during the, sorry, pardon the noise. But yeah, so I basically did a lot of internship where gradually, the one on the rightmost you see, I did an internship at IIT Kanpur where I was developing pipeline inspection robots. Then I had a very amazing opportunity to work at CMU where that was my first exposure to space robotics, where I did some work on the Google Lunar X Prize as part of Astrobotic. This was when Astrobotic was a super small team, and now if any of you are space fans, you know how big Astrobotic has grown, and they're doing some really great stuff now. So it's really great to see that progression. On the left too, what you see are some of the videos from the work I did where I was going deeper into computer vision and learning. This is a year-long work I was doing at TU Graz as a research staff, where I was really getting deep into both aerial robotics and computer vision. So gradually starting from exactly the kind of things that usually first years do with building line follower robots and obstacle avoidance, maze following, taking part in competitions, I started to get more hands-on experience. And that's really key. And I would strongly encourage all of you who are interested in pursuing a career in robotics to go out, get real world internship, real world experiences beyond what student projects can allow. Student projects are a great way to start up, getting more knowledge about it, but there is a lot of difference between working on those and then working with top labs, working at those research. You get a lot of experience with that, building real systems, and that really helped me prepare both for grad school and a career in robotics after. So that's my journey. I'm happy to really go more detail into either of these things, or in general, what's really, as a student, what are some of the to-dos and things to avoid, if you guys have questions on that towards the end. So that basically brought me to my current journey at NASA, which I joined right after grad school, where my role is really I feel fortunate to be working in this role, where my day job is to basically bring together two of the hottest technologies in the 21st century, AI and space exploration, and work at the intersection of both to enable. And in terms of not just from a technology perspective, these were also very much things I was extremely passionate about. So growing up, I was always super excited about space. I was a space nut, like they call it here, but I never thought I could, like, aerospace engineering for some reason was not something that attracted me, yet I wanted to do things for space. On this technical side, I found more interest in AI and robotics, and that's what I wanted to get to working in. And why I feel so lucky is because JPL and NASA is one of the only places in the world where I can actually pursue both of them. So thankfully things worked out and I was able to combine them. The lesson from that is just pick up the things you really, really like and just keep following that. So, so I said I do AI for NASA. Some of you might be thinking, why does NASA even care about building intelligent robots or AI? I mean, we've been building. So NASA, as we know, as we most of us would know, has a long history of building really capable machines. For 60 to 70 years, we as an agency have built spacecrafts that have visited almost all the major objects in our solar system, from the moon and Mars to the outer planets like Jupiter and Saturn. To the extent that two of our spacecraft, Voyager 1 and Voyager 2, illustrated in the image here, in the picture here, are the first man-made objects to have reached interstellar space. So growing up, all of this inspired me. I mean, this and both the spacecraft that we were sending and the Apollo missions, looking back in retrospect of videos, that really inspired me. And this is what I wanted to do. But as I started to become more of a robotics engineer by training, uh, I started to realize something different. Uh, that a lot of these machines are actually not intelligent in the way I would like to call them. So while we've been building really capable machines, uh, they have the human brain running them. So let me explain what I mean by that. Here you see two of my favorite pictures. On the left is a picture from the Apollo missions, which carried the first humans to the moon. Now, one of the critical aspects of the mission was landing, and that was made possible due to the intelligence of the human astronauts, who manually piloted the aircraft for a safe touchdown. An extremely complex maneuver that is still late very difficult for machines to accomplish on their own. We just landed the Perseverance rover on Mars, if some of you might know that, and only now we are starting to get some amount of intelligence into the machine, and this is after working on this for 25 years, and I'll talk a bit about that. But we're still a long way to go. Landing on Mars is Moon or Mars or any planetary body is one of the most critical aspects of any mission, and we've already learned that. JPL has been fortunate, and after a lot of failures, we've started to get to a point where we are starting to learn how to land successfully on Mars. But a lot of the countries, a lot of the organizations which is now starting up, you see, those are the places where we typically fail. Uh, so yeah, so that's one example of it. So similarly, on the right, you have the picture of the Curiosity rover on Mars. Now, while the rover is one of the most capable machines that was ever built, it's remotely operated by a large group of humans from the mission control room here on Earth. So every day, a team of scientists and engineers uplink a detailed sequence of actions carefully planned for a rover to perform. We basically we talk to the rover twice a day, where at the beginning of the day we send them instructions, and at the end of the day we get back data, and then the human operators here, they work in a synchronized schedule where while the rover is sleeping, we would be doing the planning for it and then sending it back the plans. Now, while this has worked so far, it's definitely not scalable for future. There's a growing need for future spacecraft to be autonomous, self-aware, and have the ability to make critical decisions on their own. This is primarily driven by two major factors. First is the difficulty of deep space communication. Apart from the fact that we are severely bandwidth limited and there is no internet for space yet, these planetary bodies are just simply very far. Uh, as you can see with the timelines here, like if you want to send a single signal to the Europe to the Mars, it basically takes almost 9 to 21 minutes, depending on where Mars and Earth are with respect to each other at that time. And this really prevents us from being able to control the robot. And this is why when we land on Mars, we call it 7 minutes of terror, because it takes 7 minutes to land, and we don't know what's going to happen in that time. And the next few decades of space exploration, at least for JPL, is going to, if JPL is concerned, is going to involve visiting the outer planets and their moons, like Jupiter's moon Europa, which is considered to be one of the best places in our solar system that might have evidence for life. For Europa, it takes several hours for us to send a signal and receive it back. So the only way we could send robots there is if they are fully autonomous, period. The second major reason is scalability. The image on the left here is a snapshot of the satellites in orbit around Earth at any given time. Now, this is a few years old itself, and with exponential growth happening in both commercial space every year. On the right, you see a vision of what Mars colony might someday look like. Now, imagine having a team of 100 plus engineers and scientists here on Earth controlling each of those small assets. It would sound crazy, right? Yeah, it is. The only way we can scale up the space economy is if we make our space assets to be self-sustainable using AI. And AI is a key ingredient. So how would AI-powered space exploration look like? To understand that, my team and me, we first mapped a few key areas for planetary robotic exploration where AI could make a 10x difference. These are autonomous navigation, think self-driving cars on Mars; autonomous science and planning, how can we use AI to do better mission operation, scheduling, planning activities that we typically do here using hundreds of scientists; precision landing, I briefly mentioned about this. So think of an autopilot that helps our spacecraft land safely to its desired location; autonomous manipulation, allowing our rovers to perform dexterous operations, not just get there and drive, but actually interact with the environment, interact with humans potentially, and be able to work in team. And that really is the next part of human robot teams. Very soon, we envision that it's not just going to be robotic exploration. We will be sending humans back to Moon and potentially Mars soon, and we'll be able to have teams of robots and humans be working together. Now, I'd like to mention that this is while there's a wide range of application in space exploration beyond robotics and autonomy uh, that applies. That's beyond the scope of the work I do, and that's why I've kept the talk to mostly focus on things that are required for robotics. So, said that, I'll begin by talking about the latest rover that we've landed on Mars, Perseverance, which landed just over a month ago. Um, on Mars, hope most of you saw the landing. It was one of the most amazing times that have been most amazing days of my life, and it was really amazing to see that thing land on Mars. And this is an image of the rover in the spacecraft assembly facility and clean room at JPL, where the rover was put together and brought to life. This is from January last year, just before the rover development was completed, and it was sent to the Kennedy Space Center to be launched to Mars. It's one of the most capable rovers we have ever built and landed on Mars. And I'm going to take this as a baseline to show you where we are and where we want to go. So these are some of the pictures from the launch of the Perseverance rover. It was launched around in the middle of last year. It's a beautiful launch, and it was just great to see some of the work we're doing being flying on its way to Mars. And very soon, we basically, this is some of the latest updates that we have seen. This was on the left. What you see is when it landed on the surface of Mars. I don't have the video of the Mars landing, but if some of you have not seen that, I would highly encourage you to go back after this talk and Google the Mars rover landing video and look up that three-minute plus sequence of video. It's one of the most amazing things you'll see. This is the first time we ever recorded. We had a camera on board that could record the descent of the rover. And so that's why we have been able to see the images on the right that you typically only see in visualizations and graphical illustration, but not in real pictures. And on the left is the first picture from the Perseverance rover that we have got. So it's great to see that the rover we built was on Mars, and I'll talk about and basically AI played a very key role in making sure that happens. And this was one of the first time we used computer vision algorithms on board. In this much amount of autonomy to allow the rover to allow the algorithms to really choose where we want to be landing. But I'll start to talk by talking more about autonomous navigation as the first part, which I spend a lot of my time on. So this is a video from some of the tests that we do for the autonomous navigation system. So now that the rover has landed on the surface of Mars, for the next 2 years, its goal will be to basically drive around on in that area and collecting a lot of very interesting science and for us. So driving is a very huge part of what the rover will be doing. So as you see here in this video, and what you see in this video is there's a graphic is a video sequence from the testing we did in Martiat, which is the JPL's mini outdoor facility, which has where we try to replicate the kind of environment we would face on Mars and do a lot of our testing for our robots there. So in this video, if you saw the rover move, that was the Scarecrow rover, which basically is an analog where we use to test our mobility systems. And in that rover, what we if you paid close attention, the video here was speeded up by 50 times. So the key thing to pick up is that the rover is extremely slow when it moves, uh, and it moves only at 5 centimeters per second. Now that's really slow. If I was, and it was almost surprising to me when I knew that, because I've always I sort of knew about it, but just when you really grasp how slowly it's moving, it's really a very limiting factor in how much we can drive. Uh, and that's really been the focus of a lot of the work I and my team have been doing. And because when we look forward beyond Perseverance, and a lot of this talk will be about not just what we did for Perseverance, but what we want to be doing beyond Perseverance, where robotics research can really play a big part in. Uh, and this and the reason we want why 5 centimeters per second is really slow is because that really limits how far we can go. Uh, with the Curiosity rover operating for almost 8 years now, we've been able to drive only tens and twenties of kilometers. But we are already for Mars 2020, which is a Perseverance rover, we are going almost a magnitude more, where we'll be driving significantly further, which the goal is to drive almost 20 kilometers in 85 sols. A sol is a Martian day, which is 40 minutes greater than an Earth day. So, but that's really what we've been doing. What we want to do in the next decade is exponentially increasing this. The kinds of mission concepts we are studying, the kinds of things in the next rovers that we want to be building, is we want to be going really far and cover a lot of ground. Consider the example on the right of a water transporter. Now imagine you want to do a human settlement on Mars. All the water is really on the poles, but it's really not feasible to send humans to the poles and build a sort of like a mini first settlement there, because it's just the temperatures and the environment is not susceptible. The equators are much more suitable for suitable for when we would want our first human sites to be settling down. So now what we would want is kind of infrastructure, and one example is a water transport system, where we imagine a robot that could go to the poles, bring water and bring it back, and a huge network of these robots that's doing this. Now these robots would be needing to transport 3,000 kilometers in order to do that, and that's just not something, the kind of technology we have. So what's really limiting us from doing that? Is it just that we don't have the mechanical systems to do it? Turns out not. We already know how to drive faster, further, and basically really go fast and long distances. And we saw this not just now, but we've solved this problem back in the 1970s itself. We had Apollo, when the humans went to the moon, we had a roving vehicle, which actually allowed the rover, which had a top speed of 18 kilometers per hour, which is almost 100 times of what the Mars rover would be moving. Now, while there is some differences between Moon and Mars that makes it different, what really made the difference was not the mobility system, because as you see in the picture here, we used a very simple mobility system. The key difference was the human brain that was running it, and that allowed it to be extremely fast in operating in its environment. Right now, the Mars rover, when it moves, it moves really slowly because it has to constantly stop to think what it wants to do to the next action. And even to think, it takes a lot of time to do some basic actions that would run really fast here. And a major bottleneck so far, leading up to even including Perseverance rover, has been the availability of space computing. The current rovers on Mars run a RAD 750 processor, and to give you an equivalent, this has the same amount of compute that you would find on an iMac G3 from the 1990 from the late 90s. So that's the amount, and this is significantly less than what your iPhone holds in your hand. So the challenge from a software engineer and a robotics researcher becomes, how do you scale up really intense algorithms to work on those? And it's always been a constant battle where we want to have more and more compute, more autonomy, more amount of very heavy lifting algorithms, but we just don't have the compute to run those on board. But that's also changing. There's been a huge push in the last decade to develop more radiation hardened computing. And one reason why this has been slow is not just because technology is it's impossible to do. It's because of the economics factors. There are not enough vendors who want to buy hardware which are radiation proof. So building even a single computer costs millions of dollars at that time, and it just doesn't come down. So that makes the whole economy slow and progress in that area slow. But there's been a lot of progress, not just in developing better radiation hardened computing, but also developing also in changing the risk posture, where there is a lot of off-the-shelf uh, compute hardware, which are now actually, we are learning, is already radiation hardened enough that we can run things on them for smaller timelines. And a great example of that is the Mars helicopter, which will be running the same processor that your phone has, which is the Qualcomm Snapdragon processors. And it's basically straight that, and we'll be using that. And there's been a great push to using these kinds of off-the-shelf technologies from commercial vendors for future rovers. So let's talk about, so now that we have more compute coming up, what are we really doing for making our rovers more smarter and faster? So there's been two major thrusts in developing technologies, and those are along the lines of perception and planning, especially using I'll be talking to you about how are we using AI technologies to improve the perception capabilities and then the planning capabilities of these rovers. So for 2 decades, we've been operating rovers on the surface of Mars, and one of the top priorities always has been safety. So how do our rover planners really navigate the rovers in a safe manner? This largely depends on images so far, both from orbiter and the rover itself. On the left, you see an example image from the navigation camera of the MSL rover. And on the right is the orbital image from where our next rover, Perseverance, will be landing on February of 2021. When the human rover drivers interpret these images, they use two kinds of information: geometric information and textual information. The geometric information maps to the surface topography. For example, on the left image, you see the local topography of where the slopes are, where obstacles like rocks and outcrops are. Similarly, on the right image, you see more of the global topology, like mountains versus dunes. In contrast, and right now, onboard our rover, we have capabilities to do these. In contrast, the textual information that the humans use maps to semantic information, like terrain types. For example, on the left image, you see regions of the image labeled as soil versus bedrock. Both geometric and textual information are crucial for safe rover navigation. However, the rovers only see the world like this right now. The current onboard navigation software on AutoNav, onboard Curiosity, and also on Perseverance only uses geometric information from stereo processing for traversability. Now, the ground software too could only process topographical information. So what could be a danger in driving this way? For example, we lost Spirit rover in sand. The Opportunity and Curiosity rovers nearly got stuck. Telling sand from cohesive flat surfaces is not possible without textual information. So we created Spock, a deep learning based terrain classifier for Mars rovers. With Spock, autonomy algorithm sees the world like this. Just like humans, Spock can tell the terrain types on images based on textural features. We developed two versions of Spock. One that works on the rover and uses 6 different terrain types, as shown in the image on the left, and one that works on orbital images and has a more fine-grained classification and uses 17 classes. With Spock, we've made an attempt to enable human-like ability for algorithms to assess the traversability and safety of rovers, driving based on topography and terrain type. Our capability has been built mostly on the ongoing revolution in computer vision, deep learning, and AI in general. In recent years, there has been a great progress in the development of CNN models for the purpose of semantic segmentation and image classification. These models typically digest an input image and output a segmentation mask with the same pixel size as the original image. We've adapted these state-of-the-art models for our use case. But these models are, of course, originally intended for classifying objects on Earth, not on Mars. So there's a few key challenges that come when we try to adapt these technologies for Earth and want to apply them to a very specific use case like Mars. And those use cases are very unique to Mars, to space applications in general. And they are availability of data, limited onboard compute, and system validation. So let's talk about data first. Like all machine learning, like people who might have worked on machine learning, they would know high quality data is extremely important and a key ingredient for good performance. For Mars, this is a problem because we just don't have big data sets like you get for AI development here from self-driving cars, from other universities. There's a lot, if you're getting into machine learning right now, you'd know there's a lot of data sets out there, but they're just not there for space applications. So that's a problem. So we basically came up with a way to solve this problem while also enabling some of NASA's goals, and that towards STEM outreach. We used multiple ways. One was we asked our experts, rover drivers and scientists on the Mars rover missions, but there's only a few amount of those people. So imagine there's probably only 10 to 15 geologists in the world who are really experts who know how to label surfaces on Mars. And imagine how busy they would be. So if you want to get their time to actually do labeling, it's just an impossible task to do it that way. So we try to go out and do a citizen science project called AI for Mars, where we use free crowdsourcing from the internet community and to label images for seen by past and present Mars rovers. How we made the geologists how we made this easy for the citizen scientists who don't know this is we worked with the geologists to create a very interactive uh, knowledge transfer, so that basically we could capture their knowledge and transfer that to a web-based tool that would allow and a nice tutorial that would allow even a kid who is studying in third grade to maybe give us some data using and go out. And this is something we did during the COVID, and we received some great feedback because and the kind of uh, what we saw was very amazing, because even like kids, we got feedback from school teachers that kids in even second and third grade were getting so much excited about, and this was giving them some joy during COVID while they were sitting at home. So, and using this, we were able to get more than 200,000 labels just in a matter of a couple of months. So this was one great way to collect some data. And while we do acknowledge that some of the data might be noisy, we are also working on techniques to how to clean out some of this data that can be used for labeling. Another way we've been starting to look into is leveraging some great development happening in the area of high fidelity simulation and generating synthetic data sets. We worked with a startup called Bifrost AI, who excels at generating perfectly labeled terrain data of complex environments and using 3D graphics. And we're looking at how can we use developments in gaming engines to basically get better auto labels for us. We use all this data and were able to successfully train a classifier to segment terrain types and Martian data. On the right, you see a time lapse of the onboard rover images from the Curiosity rover, and on the left, you see an aligned orbital image with the top-down view of the robot's view overlaid. The next challenge is limited computation, and this is a movie from our test of Spock Lite, a light version of the Spock algorithm that we ran on an analog rover called Athena. Here we try to see if we can basically deploy a much more simpler classical machine learning method that could run on very tiny amounts of compute power and do a much more simpler problem like just separating sand from the rest of them. So while we're looking at intelligent ways to scale down our models, we're also looking at hardware solutions and other innovative ways coming up such as using new devices like FPGA, AI accelerators, and even things very cutting edge like spiking neural nets to see how can we really trade off this energy, compute, and performance trade-offs for our Mars rovers in the future. The third and often overlooked challenge among AI and robotics community is system integration and end-to-end verification. So, and what I mean by that is making sure our systems really work when we get to Mars. Once the rover is launched, we do not have the ability to just bring it back, fix things if something goes wrong. We have to develop our algorithm so that it really works at one shot, which makes the stakes even higher. All of this results in a pretty exhaustive system integration, validation, and testing campaign. I can easily spend an entire hour talking about how we do this, uh, in but it really boils down to testing the recreating scenarios here on Earth on that we expect on Mars here on Earth and testing the heck out of that system. What you see here in the image on the left is a Scarecrow rover, which is the analog version of the Mars rover that we use to deploy our algorithms. And on the right is another rover called Athena that we used, that I already mentioned in the last slide. And this is a test from what we did recently in September of last year, where we've been testing long range drives over the range of several kilometers so that we can show that we can do those things and learn where things fail. So that was on the perception side. Since I'm running a bit slow on time, I'll go very quickly on the planning. So this is a very short introduction to what we have basically running currently on Perseverance rover. This is the planning system, which uses a three-tier planner. Basically, it has a global planner that tells you where should be the rover be going, and then it uses a local planner that does obstacle checks. So whether you'll be colliding with something and whether the trajectories are kinodynamically feasible. And this is the slowest part of the algorithm, and this is what drives the 5 centimeter per second, where the rover making sure each part of the trajectory is not colliding with something is extremely expensive to do. But humans do this really well. And while the must basically, and there is something like and humans have an intuition that really gets captured. So if you look in the left image here, and if I tell you where to navigate the rover, you'll pretty much be able to mark out this trajectory that says you should be going in this direction. And this is what we've been trying to do with another of our projects, where we're trying to capture this intuition to make our autonomous rovers our path planning much more quicker, so that it doesn't have to evaluate each single path exhaustively, and it has these intuitions about the world that it can use and capture. We're using this again using end-to-end machine learning. We're exploring methods of reinforcement learning, imitation learning, and classical methods, where we're using a lot of simulation data and running our rovers across different terrains, different environments, making sure, looking at failures and having the robot basically learn from its failures to what it's doing and build this intuition to where a good path is. And our big vision here is really to build something like this, an automated Google map on Mars, where it can basically, a rover, when it's on Mars, it can really, and it wants to go from point A to point B, it can have these really intelligent reasoning about how to navigate those paths without a human even interacting. So that was about navigation for the rovers. So I've talked to you a lot about rovers, but the most exciting part for me at the Mars 2020 mission is the helicopter named Ingenuity that's flying with it. This would be the first time ever we would have a powered aerial vehicle on another planet. Here's the image as you see on the actual flight model of the Mars helicopter that's on Mars right now, just before it was integrated with the with the Perseverance rover. And the most exciting part for me is it's powered by AI. So this is an illustration of how the Mars helicopter would be operating. Basically, now that the Perseverance rover has landed, the plan is for the helicopter to be deployed on the ground and then do a series of sorties where it would be using its own onboard computation, and that is powered by computer vision to basically navigate itself and localize itself. It'll be using that. So as you see in the video here, once it takes off, it has a downward facing camera, and it is using that camera to constantly take images of the environment. And that should show up in the video just in a second. So it'll be doing this. So this is a tech So here you see it's taking the images of this, and how it works is it's basically going to be tracking those algorithms, tracking those images to localize itself to where it is on the planet, and then finding a good surface to land and landing back. So this is something we're right now working on, and we're hoping to have the first flight of the Mars rover, Mars helicopter on sometime by first or second week of April. Uh, yeah, so this is actually the images of the Mars helicopter now on Mars. The last time you saw it, it was on Earth. And here, if you look at the on the left image, if you look at the belly pan of the rover, that's where the Mars helicopter is sitting. So it was covered with this debris shield. It was protected using that. We have already dropped the debris shield, and now we are working towards. In the next couple of weeks, we are working towards we can drop the rover, drop the helicopter from the rover to the surface, and then the rover will drive off. And this is on the right. You see visualization of where we have identified as the airfield where we'll be flying now and doing the first flight ever on Mars. Looking forward, we have not just been developing navigation capabilities for our current rovers, but also for future missions, which have considerably different mobility systems. What you see in the images here are concepts of future robots that we plan to send both to Moon, Mars, and beyond. As I mentioned in the beginning of the talk, the next few decades of space exploration would involve visiting the outer planets and their moons. These bodies, like Europa, have a surface made of ice, and we believe that under these ice shells, we will have water oceans, very similar to the Arctic and Antarctic regions here on Earth. So we have developing robots. We have been developing robots, like you see in the image above, that can both learn to walk, ski, or drive on ice, and also deep dive into these oceans and swim to help us find life and study underwater environments. Remind you all that needs to be done completely autonomous without a human involvement for several hours. Also, we don't really know how much of the surface and subterranean nature of these environments. We really have never seen pictures of this. We just don't know what's out there. So it's really even hard to design a robot to work in that first place because we don't know what to design for. So I see this as one of the greatest grand challenges of AI and robotics for this century. Also in the middle picture is a robot called Lemur that is being designed to climb rocks. For future exploration to Mars, now that it turns out that one place that scientists really want to go and explore Mars are the underground caves and lava tubes. Historically, we've built rovers and now we've built helicopters, but even with rovers and helicopters, it's impossible to go really close to these steep walls where the most interesting science is. And robots like Lemur are perfectly suited for such environments. Uh, so this is these are some snapshots of some of the field tests we did a couple of years back, where these are underground caves and lava tubes. Here on the left are the underground caves and lava tubes here on Earth from New Mexico, the state of New Mexico in US. And on the right, on the top right, is what you see is a similar lava tube that you would that's captured on the moon. So that's a picture from the moon that's captured using orbital images. And on the bottom right is an example of how that the rover we built we were testing those robots to climb on those surfaces. How AI is being used in this is again very similar to the algorithms like Spock, where we're using this to, rather than navigating, we are using it to figure out what are the right places the robot can hold on to the surface. So think of a rock climber with a brain that's basically trying to reason where to hold the ground so that it doesn't fall off. And this is a video of yes, this is a video of the field test. In interest of time, I'll skip to the next one. I'll probably close out with maybe a couple of more things, just to leave time enough for questions. So I wanted to talk about precision landing, but I'll skip that part out, saying that a lot of the work we're doing is in computer vision. For folks who are more into computer vision, really, precision landing and landing safely on another planet is extremely important. And it's also a very big commercial interest. So you've been seeing a lot of the technologies we've been developing at JPL has also been and found its way into what the SpaceX's re-landing does, and it's also is completely powered using computer vision and AI. And this was the first time something so critical, like a very involved autonomy algorithm, where we totally took off any of the control from the human and put it to the rover lander, was used on the Perseverance during its landing. And this is why it was such a big deal because for the first time we were able to land into an environment which is so complex. These are some of the most recent images. These are just behind the scene algorithm pictures that you would see on how it works. As it was coming down, it was basically taking images of these. It was finding these landmarks and matching those landmarks to the surface, to a predetermined orbital map so that it can figure out where it is on the surface. And this is how the hazard map looks like. So the arrow showing where we actually ended up landing on the surface of Mars. And on the right, what you see is as it's going down, it's doing that matching that you saw in the previous slide, and it's using that to figure out what areas on Mars are safe to land on. And everything that's in red here are not safe. So you can see how precise you need to be in that matching part. Sorry. So if you're off by even a small amount, you're basically crash landing, and there goes your mission. So this is an interesting thing I read was this is almost like doing a hole in the one, where your hole is basically 5 meters wide from a distance of here to Mars. So something like that, and it is a really interesting analogy of like really how perfect and precise you need to be able to do those. These are the different aspects of, again, I didn't really go into precision landing, but I want to make sure I you guys, strongly encourage you guys to go back and look at the precision landing work, the Mars landing work that was done. Look up for these things. And if you're interested in computer vision, because this is the first time computer vision has been able to enable a major space, has found its way into final mission of space. It's not just something that's good and it's making it better. It was a key enabler for making this mission happen. So one last video before I end it. So I talked about robot manipulation before. So this is also some fun work we've been doing at JPL. And this is something I really love about my work, is that we don't just work with regular robots. We really get this opportunity to build a lot of extreme robots that can take it to extreme environments and make it work in those. So this is an example of a robot that was originally built for the DARPA challenge called the RoboSimian. And we adapted that robot for space application to almost behave like a space astronaut, where someday we envision a robot like this to be building big mega structures for us. So right now, the way we've been doing things is building telescopes here on Earth. What we want to do is send small parts to Earth because that's cheaper, send small parts to space because that's cheaper, and then have a robot like this build it together in space. And those are the kinds of tests we've been doing here in lab. I'll skip this. A lot of the work also really feeds into Mars sample return, which is the next big thing for this decade. I'll skip this. And basically, for me, while I've been talking about robotic exploration, I'm personally growing up, I was super excited about human exploration, and that's something I'm extremely interested in. So some of the future work I envision would be towards enabling robots that could work with humans. And this is where a lot of the open questions are. How do we do that? How do we build robots that could reliably work with humans? So I'm looking forward to work with that, and I'm hoping some of you will join me in this endeavor. And we're always looking for really great people to work with us. Thank you, and I'll spend 20 minutes for the questions. And this is my email in case any of you guys want to reach out to me with things we can't get through with question and answer on. Thank you.
Sure. Yeah. Thanks a lot, Shreyansh. And actually, it was very elaborate and extensive. So most of our questions. So we actually floated a form, and to get questions, interesting questions that people would like to be represented here, and most of it, I'm guessing, will be answered by just listening to your presentation. So thanks a lot for that. And on that note, let's probably, in the interest of time, it will be great if you can put forward your questions actively in the chat as well as raise your hands. So let me just quickly start with a question that was greatly in the form that we collected. So what people want to know is, okay, NASA is doing all this wonderful work, and as a budding robotics enthusiast or an external person, so how exactly can he or she contribute or start contributing? And extensively, for example, currently Perseverance has 2 of these robotics arms, which are entirely autonomous. As you said, as we go farther, we need more and more automation, right? So it's an exciting time for roboticists. So what are some of the open avenues for students, or some opportunities NASA is ready to bring in? So it would be great to have your insights.
So plenty. So let me answer that in two parts. So one is what is NASA interested in? I think across the board, as you saw, there's a huge diversity of like things we work on. Pretty much anything you work on a robotics project for your robot that you want to build here, that you might be doing already in your lab, that the core components remain the same. You need perception, planning, all of that, manipulation, arm operation. So yes, all of that is interested. I think the more interesting question that you guys are interested in as a group is what are the opportunities available to you guys to get engaged in. And again, there is a lot more opportunities than mostly people think. So some of the best ways, there are a lot of, so if you, NASA is big on STEM outreach because that's one of the big mandates. I mean, it's a government agency and its goal is to really promote education. So we have internship opportunities, we have a lot of competitions. So, for example, one big thing that I'm also involved in is called the NASA Space Apps Challenge. So, it's the world's biggest hackathon where almost 40,000 people from across the world take part into this. So, those it has a lot of challenges. You can take part into those. There are global competitions. We have robotic competitions that you can take part on as teams build rovers that could take part into these things. So taking part into competitions, building technologies that would be of interest to NASA, there are a lot of that opportunities. From time to time, they even do announcement of opportunities. So I know some colleagues, some people who have basically been working on CubeSats or they've been working on certain things, and then NASA also does these zero G flights. So if you've heard of the Vomit Comet, you can basically, if you have something that you're really wanting to test, they call out these opportunities where you can apply for them. You can test your CubeSats. You can test your technology into space. You can apply work. There is, yeah. So that would be one directly would be more internships. Look for internships. Build your expertise so that it's relevant. Like if you're working on things that are relevant to us, if you have something that is very critical to NASA, that if you're building something that's going to be very important to NASA in the long run, we would be all ears. We would love to work with you. We would love to hear from you. Obviously, things get like one of the big challenges becomes the fact that, and I've gone through that, is uh, it's very limited for non-US persons, and often that boundary just becomes a problem, and it is something you'll have to fight. You'll have to fight, do 10 times more to get to that one position that would be available for none. But again, it's not a matter of, I think that those are just hurdles. There are a lot of opportunities out there. So it really depends on your interest. There are internship, again, to paraphrase, there are lots of competitions, lots of internships opportunities, lots of other collaborative opportunities to work with. Just keep an eye, be proactive to look it up. And yeah, so even if you Google NASA education, they have specific pages for how can kids at fifth grade can take part, how can kids at high school can take part, how can kids at college can take part. So yeah, hopefully that answered some questions.
Yeah, I actually answered a couple of questions that were popping up in the chat as well. So people wanted to know why is this US citizenship, is it a problem or how to fight it? And it was very clearly addressed.
Yeah,
So
so just to say on that, so again, like it's just one comment because I think it's an important point. It's limited, but it's not impossible. So I would say less than 0.5% of the people are non-US persons. So it so 50 out of 5,000 is not a great number and it breaks the odds down. But the point is, if you're really passionate about what you do, you build your expertise, and you're really good at what you do, people will make it happen for you. It doesn't matter. And it doesn't. It's not just about JPL or NASA. It applies everywhere, and that's just how the world works.
okay, yeah, thanks a lot, Shreyan. So another question, I'm not taking anything from the box. So I think Sangamitra, who's raising her hands here, I think her question is answered. Or do you have anything else? Probably you can unmute yourself now.
So I have a question.
Sure.
Please go ahead.
I'm very glad. Like I was trying to connect to you since like I don't know 6 months. I'm Sangamitra. I'm from West Bengal, and I was preparing myself for masters. So I just wanted to ask that what type of courses or what current projects should I do right now so that I can, during even I start my graduation studies at America or in US in the coming year, I could, do projects which are related to NASA or which are related to space robotics because I'm really interested in into doing that. But since here in India, I do not have that big opportunity. There are no much resources, so I cannot implement it right now. But how should I prepare myself? What should I do? I mean, what courses, what small projects, and then while coming to MS, what kind of labs? How should I approach? Some stuff regarding that.
Right. Thank you, Sanamitra, for that question. I think, and apologies if you reached out and I haven't replied to you. Sorry for that. But
Okay.
yes, so I mean, it's a very general question. So it really depends on what you're specifically interested in. I'll try to answer that question so that it's applicable to everyone. So whatever you're interested in, what aspects of, like, it can be space robotics, but it doesn't need to be robotics. It can be, let's say, you're just interested in astrodynamics, or you're interested in data science and you're wanting it to apply to space. It's more important, like, you need to build expertise and background that's relevant to it, so that shows that you have done an initiative. Interest is almost never enough. You need to, like, if you're interested, you would want to see initiatives. So opportunities might be limited, but there are, especially right now, there is a lot of opportunities. Like, you can just go on internet and do things. Like, you may not have, even if you're financially limited to have hardware to buy, you can try to work something on software. When as I've been on admission committees, and even when I'm working on trying, we're looking for interns or hiring. What we look for is what did the people do with the best opportunities they had and the interest they had. So again, that's what we'll be evaluating. So if you're interested in space robotics, there are people in India who work on it. There are even startups coming who want to work in it. Try to reach out to them, try to connect with them. Even some project, like, do something on your own. Like, even if you, like, take up a textbook and say, and you can make an intelligent comment about, okay, what did you read? That shows that you made an initiative. So it's more about, like, and that is the part, it's very hard to answer, because what you should do, because there's just no right answer. You will have to figure out, you'll have to define your own journey, I think. And the right things are, again, as going back to the same things, try to look for relevant internships. That's the best thing, because if you've worked with the right people, you've done, if you've already done the projects that I'm already looking to work you on, I mean, there is no reason I'll not get you. You'll be the biggest asset for me. So if you have the exact expertise, skill set, background that I'm looking for when I need help, I'll basically choose you. Simple as that.
Okay, so that time the citizenship won't be a problem. Like, it is a kind of a hurdle, but it is not impossible totally, because
It's
that.
always going to be, I mean, it's always going to be a challenge in terms of, so some projects are amenable to non-US persons, some projects are just not. So it really depends, and then it's a matter of timing, whether how many positions we have, how many things we have. So I'm just saying, I mean, I just cannot give you a black and white answer to that,
Yeah,
unfortunately.
definitely you can't give that.
Yeah,
So,
but I just want to say, it's not a red line. If you're building, eventually there will be opportunities that will come by.
okay, thank you so much for that answer. Really, that was
Okay,
helpful.
definitely.
Yeah, we have a couple of more hands, but so in the interest of time, probably you can take one more question, one final question, and wrap it up.
That's
So,
fine. I'll try to take, if there's, yeah, and I can say maybe a minute or two I can go over. But yeah,
yeah.
let's see.
So, okay, then let me just exploit it. So, on that note, a lot of these techniques that currently NASA or JPL is moving on is the state of the art, like machine learning, reinforcement learning, like of full automation of the robots, right? So, how much do you consider in recovery? Let's say the problem has happened, because unlike any classical control or anything, it's highly uncertain out there, right? So of course you do a lot of validation. You ensure that no failure cases are existing. But let's say there is a failure. So how exactly do you have in NASA? Do you work on some things where you think about how can we come up with some recovery algorithm, like a problem?
Great. That's a great question. So traditionally, and I'm glad, I can already see, like, some you guys are thinking like robotics researchers, so that's already kudos to you. So these are some really very, very nice questions. So right now we've been doing that manually. So Curiosity rover had its wheel stuck, and it was a 6 to 8 month effort where some of the best minds in the world, some of the world's best experts in mechanical engineering, figured out a way to reverse engineer and basically imagine a fixed broken car, and you can only remote control it using very limited instructions. you still manage to somehow change things to get it out of it. So it really, that's human brain. So what we've been trying to do, and we're hoping that's really a big push, is this idea of situational awareness, this idea of how to have onboard autonomy, onboard failure recovery. So we've been working towards, and that's again very early research. I mean, this is something even on Earth, most you'd go to a university lab and even they don't know how to do. This is like very basic research right now. We just don't know how to recover from problems. And this is some of the work I actually tried to do in my master's work while I was at Carnegie Mellon. This was a very interesting problem to me, where failure recovery. So how do you do that? And we're only starting to work on it. But there's also technology, like we are looking at methods of reinforcement learning. We're looking at methods of how you can enable a robot to explore while also being safe. So basically, you don't want it to basically do, like, how do you want to basically, let's say a human, you're stuck somewhere. What you'll do, you don't know what to do. You'll try to poke around. You'll try to see things. Okay, what works, what doesn't work. While you'll also want to be safe, so you don't want to injure your arm or leg. So that's the kind of skill set we want robots to do, and we don't know what's the right way to do it, but we're doing research on that yet. So it's an open problem, and for NASA, it's extremely interesting and not interesting, but required, because if we want to go to Europa, we need that. We do not have the time to send back, or we do not have the 6 month time period. A lot of that mission is envisioned to be 20 days long. So if we basically don't have that capability, we just cannot go there, or the mission will not be a success.
Right.
So maybe you can club one or two of the similar questions and put it out, so that way I can answer those, maybe if there's something more like that.
For sure. So in the chat box, there are a few more questions. So Mainak out here is asking more insights into the Spock. So how exactly do you, if I'm trying to rephrase it, so he's just trying to understand how exactly you navigate through clay or sand. So what are the sensors involved? A little more.
So for that one, and in the interest of time, I'll just say Google Spock JPL, and we have a couple of papers on it, and that should really, or reach out to me and send me an email. I can send you much more materials, and it's online. So if you're interested in details of any of the work I had or things I could not cover, feel free to reach out to me on email, and I'll be happy to work with you on that.
For sure. So yeah, I think we are right there. So thanks a lot, Shreyansh, for your time, and it was very extensive. Thanks a lot. And personally, as a robotics research group, right, we came to know the different avenues that we can build up our careers, our interests, and things like that. Be it legged robots, be it a rover, or be it flying robots, or whatever it is, and what are the open challenges. So we can now start, like, take baby steps and try solving it, or try understanding it from a researcher's perspective. So thanks a lot. Thanks for your time again.
Thank you so much for you guys for inviting me. I think these were some really good questions. I can see that this robotics group, you guys are all amazing. Like, you guys are doing great work. You're not just interested, like, you're really in there, like doing the kind of work that you would be doing at the top level. So keep doing this amazing stuff, and I'd be happy to, like, collaborate, work with you guys. Like, if there's something I can help even beyond this, like, I'd be happy to connect and, like, give back, because I know this is, as students, it's not easy to do research at that level. I know it requires guidance. It's very tough trajectory. So definitely I'll be happy to provide, and more specifically about questions on NASA work here and what we're doing, how to get here, opportunities. I'll be, again, feel free to individually reach out to me if there's something you're interested in.
For sure, Shreyansh. We are also looking into space exploration, so possibly we'll get back to you with some interesting projects of ours, and we can definitely collaborate. We are looking forward to it. So thanks a lot, everyone, for joining us this time. So it's around night here, so probably we can wrap it up with this. So yeah.
Sure. Great. Thank you, Shreyansh, for joining. It is really good, and thank you for coordinating with all of us like from the beginning. Yeah.
Thank you so much, Pratyush, and thanks everyone for taking out time to listen to me.
Yep. Thank you. Bye.
Yep. Bye.